Alright guys, the next video on the journey through complex numbers. So I think the climax of the last video would have been Dewey's theorem. So if we have some complex number and we're written in polar form and we want to raise it to some power of n, then all we had to do was raise the modulus, or the modulus r to the power of n, and raise the modulus to the power of n and multiply the argument by n. So I've actually dropped an n there. So how can we use Dewey's theorem to find the roots of complex numbers? So say I've got some number, some complex number w, and it's raised to some integer power n, and that gives us another complex number z. So for example, I might take root 2i, raise it to the power of n, and that equals -8. So, or should say it's actual some other number. I don't think that's true, but equals -8. We want to be able to solve these sorts of problems. So let's put both w and z in polar form. So w is s times cosine phi plus I sine phi. And let's let z equal just our standard equation, r cosine theta plus I sine theta. So by Dewey's theorem, if we raise w to the power of n, then we're going to get s to the n times cosine n phi plus I sine, I keep dropping that n there, times sine n phi. Okay, but this is equal to z. So z is r cosine theta plus I sine theta. So we've just rewritten this equation, one complex number raised to the power of n equals another complex number, and we've just written both of those in polar form and then applied Dewey's theorem. So what does this mean? Well, we can see that s to the n is equal to r by just comparing the coefficients, and so this implies that s is r to the 1 over n. Okay, and we have this fact, and cosine n phi equals cosine theta, and similarly we have sine n phi equals sine theta. But we know that cosine and sine have a period of 2 pi, so I might actually make a wee side note. Period of 2 pi, that means they repeat. Okay, they're going to cycle back around after 2 pi rotations. So that would mean that n phi is equal to theta plus 2k pi. So n phi would then just be theta plus any integer value of 2k pi. And if we just want to write theta as, phi, as always Greek letters, as theta plus 2k pi all over n. So I've got a highlighter. This is a key fact, and this is a key fact for us. So what is that? So, Mr. Kyle, what have you shown me here? Well, I've basically just shown you that if we have a complex number raised to some power equals some other complex number, then after a bit of this working, you might want to just re-watch, then we can see that there is an easy, or is a simple relationship between the arguments, and there's a very, very simple relationship between the modulus. And this is the fact. I've just pre-written it just so you don't have to watch me do it. So, roots of a complex number. If z is written in polar form, and we're just letting n be some positive integer, then z has n roots. And those roots are in this form. R to the 1 over n. And you can see I'm just replacing phi with theta plus 2k pi over n. So all the roots, wk, is r to the 1 over n times cosine 0 plus 2k pi over n plus I sine theta plus 2k pi over n. And k just goes up 1, 2, 3, all the way up until we get just one less than n itself, because at n it's just going to repeat back at 0. So 0, 1, 2, 3 up to n minus 1. Okay, hopefully that's going to make more sense when we do an example. So, we'll do this example. So find the 6 roots of z equals -8. And although it's a purely real number, this is still in the complex plane, isn't it? So, and we want to graph these in the complex plane. So we can go z in trig form or in polar form, 8 cosine pi plus I sine pi, because on that complex plane we want z to be -8, which is over here, -8, which would be 8 times cosine theta plus I sine theta, but with that half rotation, just so we can keep that 8 positive. So there we have it, there's z written in polar form. And so using this equation here, we can actually find all the roots. So w sub k, because that's what we're going to be counting, is going to be 8 to the 1 over n, 8 to the 1 over 6, times cosine theta plus 2k pi, so theta in this case is pi plus 2k pi all over 6, plus I sine, same thing, pi plus 2k pi all over 6. Okay, to get the 6 roots, we're just going to go from 0, 1, 2, 3, 4, and 5. So w0, so our first root, 8 to the 1 over 6, cosine 0, so just pi over 6, plus I sine pi over 6. And then using your trig identities, write this in your standard form. Well, that 8 to the 1 over 6 is actually the square root of 2. So that's why I've had you guys doing some surd work before this. And cosine pi over 6, well, that's root 3 over 2. And sine pi over 6, well, that's 1 over 2 from similar triangles, plus 1 over 2 I. So there's our first root, w1. Again, 8 to the 1 6, cosine pi plus 2 pi, so 3 pi over 6, plus I sine 3 pi over 6, which is pi on 2. And we know that cosine pi on 2 is 0, but sine pi on 2, well, that's 1. So this is just going to give us root 2 I. w2, 8 to the 1 over 6. Cosine, might try and simplify this one straight away. 5 pi on 6 plus I sine 5 pi on 6 is going to give us root 2 negative root 3 on 2 plus 1 on 2 I. And that's interesting. You can see here that there's some sort of symmetry happening, and we'll discuss that in a second. So we'll just put that away. W3, W4, W5. again, 8 to the 1 6 for all of those. And then we're going to have cosine. And can we see a pattern? Right, 5 pi on 6. Yep, we're going up in 2s here. So 5, 7 pi on 6 plus I sine 7 pi on 6 cosine 9 pi on 6, or 2 pi on 3 plus I sine 2 pi, sorry, 3 pi on 2, 3 pi on 2, early in the morning, cosine, and then it's going to be 11 pi on 6 plus I sine 11 pi on 6. So they're just going up by 2 pi on 6 every time, aren't they? These are going to be, W3 is going to be root 2 minus root 3 on 2 minus a half I. W4 is going to be negative root 2I, and we're going to get root 2 root 3 on 2 minus a half I. So that's how you would get all of those roots. I'm not going to bore you with those similar triangles. You should be all good with those now. But notice that the argument is the same for all of them, and they're all only separated by 2 pi on 6, or pi on 3. They're going up by pi on 3 from in each consecutive one. So if we were to graph these, it would look something like this. I'm not going to, W0 is root 2, so the radius of this is root 2, and we've got root 3 over 2 in the real direction and a half in the imaginary direction. So that would give me W0. Then W1 is just the purely imaginary, root 2I. Then we've got kind of a bit of symmetry happening here. And these are all separated by the same angle. Okay, so they're equally spaced as well. So that might be a bit of a note that we'll want to take down. So each of the nth roots of z has a modulus, right, absolute value wk for whatever k we're choosing, of, and its modulus is r to the 1 over n. Thus, all the nth roots lie in a circle. That's what I've just shown you here, of radius r to the 1 over n. And since the argument of each successive root is separated by 2 pi over n, or for us it was 2 pi over 6, pi on 3, then we can see that nth roots of z are equally spaced. So you can see that there. Equally spaced roots, and that's going to always happen. Okay. So hopefully that makes sense. That is how we find the roots of complex numbers. I made a couple of little errors in there, but let me know if you have any questions.